Good morning, good afternoon, good evening, depending on where you are in the world. As Omar said, my name is Ashish, and I lead the synthetic data research effort in perception team at Cruise. And as Cruise scales to new platforms and new cities, we'll talk a little bit more later in the talk. Our team is mainly focused on enhancing the quality and, of course, the usability of synthetic data to improve mainly perception models, but ML models in general. As many of you know, Cruise is a leading autonomous driving company, and our mission is to safely connect people to the places, things, and experiences that they care about. And our self-driving cars are already running in major US cities, such as San Francisco, uh, without any safety drivers and with paying customers. In fact, 2022 was a momentous year in driving our mission forward. We launched fully driverless ride-hail services in San Francisco, expanded to Phoenix and Austin, and grew our delivery partnership with Walmart, all while driving impact in every market we operate. Last year, we accumulated more than 800,000 driverless miles, and more than 10,000 of these drives received 5-star rating. It's a lot of time given back to our customers. Our goal is to provide trusted mobility solution that connects communities and is safer and more sustainable. And last year, 94% of our first-time riders said that they trusted Cruise. 84% of them felt safer at night in San Francisco while riding in Cruise AVs. 89% of them said Cruise is a good driver, of course, and 82% of them said the rides were more enjoyable than traditional ride-hail services like Uber and Lyft. And we are also using driverless rides for delivery. This may be a lesser known fact. In fact, Cruise has partnered with Walmart to deliver thousands of orders in Phoenix area. And last year we completed more than 19,000 driverless deliveries. We're making rapid progress and completed, I'm super excited about this 1 million driverless mile in February of this year and 2 million driverless miles just last month. And in fact, our second million driverless mile was 5x faster than the first one. So we're not only making fast progress, we are really able to accelerate as we scale. And statistics have consistently shown that a significant number of accidents on roads are the direct results of human error, whether it's a momentary lapse in concentration, fatigue, or simply being distracted. These factors contribute to unfortunate collisions. Our AVs are not only designed to provide delightful and time-saving experience, we prioritize, of course, safety above all else. And when compared to average human error, our AVs have proven to be remarkably safer in preventing collisions. In the field of AVs, where the stakes are really, really high on public roads, we have to go beyond the basics of detecting regular objects, vehicles, pedestrians, and bikes on the road. And of course, accurately identifying these objects and reacting appropriately to them is crucial. But state-of-the-art ML models and large data sets have already enabled us to excel in that aspect. The true challenge lies in handling the long-tail scenarios that pose very unique complexities. For example, imagine encountering animals or a person running in the middle of the road close to AV, or traversing through dusty or poorly maintained road where visibility can be severely limited. Or a person loading an object in the pickup truck, which would be protruding, and the person is in a very unique pose, or a ramp on the towing truck, the vehicle appears in a very slanted angle and might be difficult. Or a scenario where a parked vehicle suddenly opens its doors, and it happens a lot. We all have noticed while driving, and obstructs the path for AV. And despite these inherent challenges, our AVs have demonstrated remarkable success in navigating through highly complex scenes. And here's an example of a densely populated scenario during an event on St. Patrick's Day, where you can see many people and vehicle are moving in various directions and simultaneously. And of course, we design our AVs to prioritize safety above all else. We ensure the movements align with traffic regulations, respect pedestrians' right of way, and in general have overall situational awareness. You can see our AVs can find gaps, adapt their speed and acceleration and trajectory to ensure a smooth and uneventful progression through at least this crowded environment. And we do a lot of testing, real-world deployment, and have fine-tuned our AV system to excel in these kind of challenging scenarios with superhuman driving skills. Up until recently, our fleets consisted of modified Chevy Bolt cars that served as the foundation of our AV technology. And these vehicles took us on countless journeys, accumulated millions of driverless miles. And building upon this experience and insight, which is very important, gained from those miles, we have designed an entirely new car with autonomy at the center of the design. And we call this Origin. And with no steering wheel to hinder interior layout, Origin offers a spacious and very inviting atmosphere. I believe we probably might have it in our booth. And passengers have, of course, ample room to spread out and making the ride super comfortable. In addition to our operations in SF, we have proudly expanded our AV services to several other prominent US cities. We successfully launched in Austin and Phoenix. And this year, we're going to launch in even more cities. I'm super excited about. Of course, these vibrant cities provide diverse and dynamic urban environment and present us with very exciting challenges as well as opportunities to showcase and, of course, improve our capabilities in AV systems. But make no mistakes, I mean, scaling to new platforms and new cities brings a plethora of challenges. It's not an easy task, but at the same time gives us a lot of opportunities to innovate. New domains have very small data, if any. When you go to new cities, for example, this makes to train the models that can generalize well on the target domain very hard. And there are, of course, long tail cases that we talked about, which you might not have observed in the current OTDs. For example, a pedestrian on the ground or someone sitting on the chair on the sidewalk. We can address, of course, the data scarcity problem with simulation, and we heard a lot about it in the previous talks. And we also heard there is usually a sim-to-real distribution gap. And sim-trained model usually do not generalize as well as the real trained model in the real-world deployment. Of course, we can use domain adaptation techniques, and they do work well, but there's a sim2 real gap that we need to be super careful about. But sometimes new platform can have new sensors for which you do not have the corresponding data from the old sensors. Or there are sensors like LiDAR and radar, which are not as well studied as the images in the community, so it might be even more harder. But despite the sim-to-real gap that does exist, and we keep working towards fixing it, simulation is an effective tool to train and test our ML models, especially as we scale and may not have enough time to collect real-world data for all edge cases. Edge cases are the key. And when we go to new cities, simulation, of course, in our case, starts with the technology which we call WorldGen that can procedurally generate entire cities. Here you see famous Alamo Square Park in San Francisco. And by combining multiple sources of data, we can build seamless map ties across large geographic area. WorldGen starts with, of course, road geometry, paint, and then adds the video is super choppy here. It adds in like curves and ramps, footprint accurate buildings, and then traffic lights, and other objects like parked cars, pedestrians. And then we can add more incremental details. So, for example, like let's say staircase in the on a park. And we can build this intersection and the entire city without much manual effort. So it allows our engineers to test models in a realistic environment in a large scale setting. And after we build the city in WorldGen, we need to make sure it looks extremely realistic, even when the environmental conditions such as lighting change. We accurately sample lighting at different times of day and weather conditions. We sample actually up to 24 times of day, like sunset on a winter day at 2 p.m. in the autumn, and of course the nighttime. We also systematically measure light from different types of street lamps on the city. And this data, of course, with the our ability to procedurally generate cities helps us to expand with efficiency. Although in the example so far, I have only shown visual data, but we put in the same amount of effort in simulating all other sensors, such as LiDAR, radar, and many more. And we use the simulation technology to continuously measure our performance on key metrics such as safety, comfort, and end-to-end behaviors. And with every software release, we run hundreds of thousands of simulation to predict performance and, of course, protect against any regressions. So far, we have discussed the process of city creation and object placement. But to comprehensively evaluate the behavior of our AVs, it's crucial for the objects within the environment to react dynamically to AV behavior. And to achieve this, we use a combination of road data and machine learning, including reinforcement learning, to model the behavior of these objects or NPCs within our simulation. These NPCs are designed to mimic real-world objects like vehicle, pedestrians. And in this visualization, the road data is represented in blue boxes, illustrating poses of all the objects. And the red bounding boxes depict the objects moving with the learned NPC model, showcasing the NPC model here is able to mimic the real-world distribution. But more importantly, the NPC should be able to respond appropriately to the action and movements of the AV. So for instance, in this specific example, we observe that the red box, which is representing the NPC, slows down in response to the decelerating AV, and AV here is shown as the solid red box. And with our NPC model, we also have implemented various adjustable parameters or knobs, and these knobs enable us to modify the behavior of or the policy of the NPCs according to specific characteristic. So in this video, we show an example of how these knobs can be utilized to test our AVs against an aggressive NPC. The standard NPC here is represented by red color, excuse me, while a more aggressive NPC variant is depicted in green. And we have turned up the aggressiveness knob for the NPC cutting into the AV's desired path. I showed in the middle of this video, actually, I wish I could point. And the ability to fine-tune the NPC model through this adjustable knob, of course, lets us simulate diverse scenarios and realistically evaluate how our AVs would behave in response to various types of NPC behaviors, because you never know what happens. The world is quite unknown out there in the public roads. Okay, synthetic data, of course, plays a critical role in perception tasks. Particularly when expanding operations to new cities. For example, when I go from a city like San Francisco to Austin, we see a lot of changes. We're going to talk a little bit more in detail in the next slide. Of course, synthetic data also proves especially valuable for dense labeling tasks, like depth prediction from images, where obtaining accurate label is actually very difficult and expensive, and sometimes not even possible. And when adopting a new platform for autonomous driving, effectively utilizing the label data from old platform. We don't want to throw away all the data that we collect just because we have a newer and better platform. That becomes very crucial. And simulation also plays an important role there. So let's look at these technical challenges and simulation as potential solution in a bit more detail. When expanding our operations, from a city like San Francisco to another city like Austin, we often encounter variation in the environment and types of objects. For example, we find that EMVs, the emergency vehicles in Austin, are different than in San Francisco, and our training data may not have seen those types of objects and then may not generalize. Of course, advantage of simulation is its ability to quickly generate these diverse assets, and that can represent the data distribution in the new city. And this synthetic data allows us to make our model more robust without having to do a large amount of targeted data collection. Long tail scenarios, which are crucial for success of our AVs, but are difficult to encounter on the road, they can be effectively generated in simulation. And in simulation, we can actually create these diverse and more complex scenes than the ones that we encounter on the road, and then systematically expose our ML models to these challenging scenarios and make it more robust on public roads. Another example of simulation use case is obtaining dense annotations, such as I said earlier, pixel-wise depth values for training, let's say, an image to depth model. And depth levels is extremely challenging and costly. But leveraging SIM, we can generate this large-scale data set with accurate depth labels, enabling us to train a depth prediction model. Here we show an example of a SIM-trained depth prediction model that can accurately predict depth of a real image from road camera and help us in avoiding critical near-field objects. When scaling our AV technology to new platform, we of course often encounters a significant distribution gap due to difference in sensor configuration or hardware capabilities or sensor noise models and etc. But we can take the road data from the old sensor, right, and render it in simulation using the new sensor configuration in the simulation. And we can use the new sensor models and new sensor characteristic, everything in simulation. And this way we use the synthetic data, the generated synthetic data that can capture the scenario complexity from the road, right? Because we use the road data to create the scene in the sim, and sensor models and sensor characteristics from the simulation. And to enable that, we use a system that we call road to sim, which can take a road scene, find the map location of it, and we have the vergen, so we can go in that vergen's location, and we can compute the pose and shape of all the objects present in the scene, either by running our perception stack or from the ground truth labels, and then render the scene for all the sensors inside the sim, of course, using the vergen. And here's an example of road scene on the top and a corresponding road to sim scene rendered by the simulation at the bottom. And for scaling to new platforms, we can render the scene using the data from old platform and then change the sensor in the sim for the new platform. But if you look closely, there is a sim to real distribution gap here too. Nothing is perfect. And the render sim data, which is not perfect, it can reduce the confidence in testing and decrease the efficacy of model trained on simulation data in real world deployment. So we need to address this real sim to real gap. So let's focus on bridging this distribution gap through domain adaptation. So sim to real transfer utilizes these translation methods, which are broadly divided into two main categories, paired translation and unpaired translation. Paired translation, of course, requires a perfect pixel match and is suitable for things like semantic segmentation to image, because you can get semantic segmentation from images and you can make those pairs. But in general, it's difficult to apply in practice because we don't have this pixel-wise correspondence between simulation and real-world data. Unpaired translation, while more suitable because you just have to have set of sim images, set of real images, they're there, but still challenging in practical scenarios with complex natural scene, and we'll see some examples what the challenges are. So to address these challenges, we propose a third category, which we call approximately paired sim to real translation, where the source and target images do not need to be exactly paired. And our approximately paired method, which we call AptSim2Real for short, exploits the fact that simulators like our road to sim can generate scenes loosely resembling real world scenes in terms of lighting, environment, scene composition. You can just put the objects wherever they are in the road and try to match their appearance as much as possible. Here are some of the qualitative results. The left column in the figure depicts the simulation images, which exhibit several subtle domain gap in terms of, if you notice, the foliage, the tree, the road color, and sharpness, contrast. Try to match it as closely as possible to the real image, but they are never perfect. For example, if you see some sample real image on the road and the right column, and we'll see later that these real images actually do serve as a style input in our approach. Our approach depicted here in the middle column is capable of effectively bridging this distribution gap to a much better degree and enhances the realism of the simulated images compared to the images on the right. For example, you can notice the color of the trees is matching much better. The color of the road is looking much closer to the real images and things like that. And of course, the contrast, brightness, everything is much better. Here we show some comparisons between the proposed AptSim2Real method and other existing approaches such as cycle, GAN, and cut, which are unpaired methods. We train, of course, these baselines with multiple sets of hyperparameters, and here we're presenting the best result we could obtain on our data set. But there are a lot of artifacts, and that's the problem when you apply these methods in the real world scenarios. For example, in the left, you can see on the traffic light, there are a lot of high frequency artifacts, and that might have a problem for the downstream task. Remember, we want to use these images, these data for training our models or testing our models. And then these artifacts actually uh, do not help in making the model more robust. Actually, they actually hurt the performance eventually. You can see there's a checkerboard pattern. Sometimes things are with the cut are much more blurry. In contrast, if you see the images on the right, AptSim2Real, I don't know how well you can see, at least in this room, the images, you can take my word for it. It will look much better, at least qualitatively. So to leverage, so let's focus a little bit more on detail. To leverage this approximately paired data, remember the approximately paired data is easily available because we have a bunch of road data. Instead of just taking it unpaired sim, we just generate the sim with road to sim to make the pairing. We train a style encoder S to extract style code from the approximately paired inputs, to input sim and real. And during training, we condition this generator, G, on the difference between the input sim and the target style. And the difference in style features reflects kind of the realism gap between the images. And we use a lot of content regularization losses, and there are a lot of, we'll talk a little bit detail later. And there are some pooling layers in style encoders to minimize any content leakage. During inference, remember, during inference, we don't have approximately paired data. We have just a lot of sim data. If we had approximately paired data, we would need sim. So we need, and we just use an unpaired real image selected from training data as the target style reference. And we compute the difference between the sim and real styles and use the style difference, of course, along with the input sim image to generate a more realistic image. Of course, since we want to change only the style of the sim image, we add multiple content losses to keep the content between the input and the generated image the same. And we use a few of them that I'll describe, but of course you can add more. And we want the style of the real image, the input reference, and the generated image to be the same. So we add some more additional style losses during training. And we'll get there in detail. Also to avoid any degenerate results, because one trivial solution for style encoder when you're minimizing the style code is to just generate zeros or some constant vector. And to avoid this, we add binary cross entropy loss between the sim and the real style input, make sure that styles do not map to a constant or zeros. So let's look at these training losses a bit more in detail. The first one is, of course, a standard GAN loss. We use LS GAN loss, where the discriminator predicts 1 for real image and 0 for fake or the generated image. While the generator tries to fool the discriminator, we optimize this G and D in alternate fashion. And I think one additional detail is that we update our style encoder along with the generator. For style loss, we use a simple L1 loss between the styles of the approximately paired real input and the generated output, and style encoder uses a lot of pooling layers. And for separating the style, real styles from the sim style, we use, as I said before, standard binary cross entropy loss to avoid these constant vector solutions. And to ensure that we change only the style of the sim image, we had several content loss. We want to keep, we don't want, for example, our goal is not to move one car from this location to the other location. Our goal is to only change the overall style. The first of the content losses is a standard NCE loss that has been used in cut paper. Essentially, it makes sure that corresponding patches in the sim image and the generated image look similar, while the non-corresponding patches do not look similar. The second one is the identity loss to ensure that the output doesn't change too much from the input. Of course, we keep the lambda for this loss a little small because we do want to change the output. This loss has been used also by many of the papers, including SimGAN. The third one is a novel loss, which we call luminance loss. The intuition is that while changing the image style, the most of the change we want to make is in the color while keeping the luminance more or less the same, right? But I'm hand waving because we do want to change the contrast and the brightness a little bit. So instead of regularizing pixel-wise luminance value, instead of regularizing pixel-wise luminance value, we compute their normalized statistics over patches. And we find this loss to be actually very useful in minimizing artifacts. So here Lx is the luminance, is the Y value of the image. Lx bar is basically you take this luminance image, pass it through some average pooling layer or 16 by 16 patches. And mu and sigma is just the mean and standard deviation uh, of that average pooled image. And we normalize it, and this loss helps. By the way, this paper is available on arXiv too, if you just search for AptSim2Real. And to verify that our style vector is not a constant vector, we show a sim input here being modified by a sim image on the top row, and the same input being modified a real image. And we can see that the real style input actually makes the changes that reflect the styles of the real data, while the same input does not change the output much. We compare this FID score of also of our AptSim2Real with the state-of-the-art unpaired translation methods, only cycle, gain, and cut. And because of better visual quality and fewer artifacts, it's not surprising that the FID score of this APT method is better. Although I described Sim2Real domain adaptation, we can apply similar method to domain adapt data from old sensor to new sensor. Right, as we see that usually when you go to a new platform, you improve your sensors, images look better, but your model does not do well on that better looking image. But how do we create these approximate pairs? That's the question. And one thing you can imagine is you can take both the sensor and then put them on the same car and drive it around and collect a small amount of paired real data from old sensor to new sensor. And we applied this AptReal2Real in this case, because the data from both real sensors. And then you apply this AptReal2Real model on all your training data, which you have spent a lot of time and money on to get labels. And then you have a new real data, which is much closer to your target domain. And we do exactly that. So here you see image from the old sensor and style input from the new sensor. And you can see the generated image looks much closer to the new sensor than the old sensor. We can also look at a more focused and safety critical applications such as traffic light detection and classification. And we can see that sensor change may result in color change and some artifacts such as halos in the new sensor. And using AptReal2Real this time, we can see the model is able to effectively bridge this distribution gap from color change and also able to have halos similar to the ones present in the new sensor. And by adding this real-to-real data into our training set, we could actually improve the performance of downstream tasks by more than 40%. And this APT or AptSim2Real and AptReal2Real methods have become a very useful tool at Cruise, not only to bridge sim-to-real distribution gap, but also to effectively utilize all the label data from old sensors. With that, I'd like to, I know I'm standing between you and your lunch, I'd like to thank you all for your attention and thank all my colleagues and collaborators without whom this presentation wouldn't be possible. I'd like to encourage everyone to visit our booth starting tomorrow and learn more about us. Also, if interested, please get in touch with our recruiters. We are, of course, hiring for many open ML roles. Thank you.